Good afternoon. This is Schweitzer, and we're looking to look at intermolecular forces. This is what this is a big topic here, which is basically why do molecules stick together, and what happens when they stick together. So, why would two molecules attract? Okay. What about why would cause it to gather electrons? So if we have x bonded to y, so that's inside here. So we have x has a nucleus, and y has a nucleus. These positive charges, they can't move. Electrons, however, they can move easily. So for whatever reason, let's say y is negative. So not a huge negative, just a partial negative, and it's a little symbol we use to describe a partial charge. So it looks like this, and it's a lowercase symbol of the delta sign in Greek. Negative means partial charge. Partial. Partial charge. Happens to be partial charge negative. Is it a full negative one? No. Right? Just a slight negative. How can this possibly be? They have protons here and electrons are on the outside. Why aren't they balancing to neutral? Well, it turns out that for some reason Y is attracting more electrons around it than what say what X. So they're sharing electrons, but for some reason when they share, more electrons are heading towards the Y than X. Sometimes I make this a scenario where, like, when you have a car and you have a sibling. When I was a kid, I had to share my car with my brother. So we only had one car. Sometimes I drove it, and sometimes my brother drove it. And it seemed like my brother drove it almost all the time. Okay. So with that being said, what about Y is causing it to have more electrons gathering around it? So we have normally be equal. This I should have redrawn this thing here. So let's start out normally. Positive, positive. Normally it's like this. Okay. And then the new version, let's do this. Let's back it up here. I'm going to draw this normal version. Okay. At nucleus, nucleus. Normally it's, just evenly spread out. That's fine. But for some reason, this is causing this side to be partial negative, partial positive, because electrons are being dragged over. So that means that in this case, I could have another situation where this is the y and this is the x, where more electrons are traveled over here and less over here, and this becomes partial negative. This is partial positive. This is partial positive, and then we get this attraction between here. We call this attraction between molecules, because positive and negative attract by Coulomb's law, force equals positive, negative divided by the distance squared. All right, that's attraction. We call this intermolecular force. So intermolecular force. Much weaker than a bond. So, but the bond on the inside, this guy right here, okay, or the sharing between, we call that's a covalent bond. And we would refer to that as intramolecular force. Intra, that's an A. Intra means within. So there's, for example, there's an intranet, an internet. So intrastate commerce, there's interstate commerce. So these attractions cause water molecules to stick together. And here's an interesting video showing how water acts in space and how we can just see these water molecules just literally sticking to one another. Really fascinating. The force that we're actually dealing with here in terms of water is what we call hydrogen bonding. Hydrogen bonding is a form, you've all heard of hydrogen bonding, but this basically is where you have this is called a dipole, so there's a term here where it's got a positive and negative called a dipole. So lots of little notes here. So when two dipoles attract, we call it a dipole attraction. Real simple, right? Just two dipoles attracting, so they call it a dipole-dipole. We've seen ion dipole, I believe, or we will see it as well. But that's just a form of hydrogen bonding. Or I should say hydrogen bonding is a form of dipole-dipole. Okay, they're very similar. All right, let's flip over to the next page. Inter versus intra. Okay, so this is not in your workbook here, but you get a good example of it. This is the inter between, that's this guy. Intra is the actual covalent bond. Next up, okay, so why do we care if molecules stick together? How does it impact our everyday life? So when molecules stick together, okay, we don't want to show a full dash, just IMFs they call them, okay, and this controls everything in biology, all right, everything. So for example, nerves firing, okay, breathing, things transferring around in your body, sugars moving between. It controls whether things are solids, liquids, gases. It controls digestion through your body. It controls everything from, let's say, how drugs are processed through your body. Everything in your liver works based off polarity. It's amazing, everything. Okay, so everything in our lives is really governed by intermolecular forces. We're never going to be really breaking too, I shouldn't say we do, but we're not breaking that many of the inside bonds. The intermolecular ones are really ones that are breaking, but I shouldn't say that. There's plenty of those broken too, but these IMFs are super important. All right, so next, okay, what does it mean to be polar? This is a term use the term dipole already. Okay, that's a term we've used. So what does it mean to be polar? Well, anytime you have a dipole, we say it's or polar. Another name for this would be called a dipole moment. Now, a dipole moment is like a numerical, number value of how polar you are. If you have a dipole moment that equals 0, well, then you are not polar. Not polar at all. You'd be considered what we call non-polar. And it's not like you have a switch that turns on and off. It's definitely a gradual. There are things that are extremely polar and things that are not so much. All right. Again, magnitude, dipole moment. All right, so how do we quantify this? Well, it turns out that there's a thing called electronegativity. And we're looking at the differences in electronegativity. So, like for example here, if I wanted to calculate out the electronegativity difference between nitrogen and nitrogen, I look at my two values, go in the chart, I find it, here's 3.0, I subtract the two values for that bond. So it's going to be 3 minus 3 equals 0. This thing is a 0 dipole moment, okay? So this is non-polar. It's not at all polar. Partially because they have the same exact dipole moment, the dipole electronegativity. Here's a scale. I wouldn't necessarily write this down, and this is something that just so you know, there's a way to calculate it. Okay, probably never going to ask you to really do this, but just so you know, it's being done all the time. So hydrogen, oxygen. Now we'll do it twice, once for this bond, once for that bond, but you'll see they're the same. So what's oxygen? Oxygen's 3.5. 3.5 minus hydrogen 2.1. 2.1. So that's got a little bit bigger value here, and be one. This would be a 4. This would be a 1. 1.4. This falls in the polar covalent range, which means that they're sharing, yes, but the oxygen is a little bit more needy, which forms slightly more electrons on this side than this side. And that is how we would encourage this guy to be polar. Okay? It has a dipole. It has a dipole moment. What's the dipole moment? Dipole moment is 1.4. Okay? Each side gets a dipole moment. All right. So that's how we quantify it. Is there a way? Well, here's that again. Okay. Is there? How does a molecule become polar? Okay, we did that right. I have this thing right here in the next slide, what are called stealers, and we'll see that in a moment. NOF. These are extremely electronegative atoms. I mean, I call them stealers. Not something that most people would call them, but I call them stealers because when they're bonded, they're constantly stealing electrons towards themselves and making them negative. Okay. Either way, how do I determine dipole moments or polarity without doing math? Okay. Well, first of all, how do I get a dipole moment of 0? That's pretty common. So if you have the same atom, for example, or oxygen, we don't even care what they are. They're the same. So dipole moment of 0, nonpolar. Okay, well, what if I want to figure it out when it's not like that? If I have a dipole moment, how can I know if it's a significant amount of dipole? So I don't want to have to do this every single time. I don't want to have to go through and add and subtract everything up. I don't want to do that. Is there a way that I can is to know it's there and know if it's a significant level? So first of all, if you know now that this gives you 0. Okay, so here you're not 0. You have something. So there are two different atoms here. How do we know if it's significant? Well, we're looking for example, let's say SO2. Looks like this. And it's got a double bond here. How do we know if this is a significant dipole moment? What we do is we just keep our eye on these guys, N, O, and F. Anytime you have one of these guys bound to something else, then we know that this is highly electronegative atoms will be negative. So this guy doesn't share nicely with the sulfur. So this guy is going to be partially negative here, partially negative here. And there's actually pairs of electrons here. And therefore this side is partially positive. This guy therefore is polar. So whenever I'm looking to see if something's polar, I'm really looking for one of these guys. Okay? Now shape plays a role, especially in small, simple molecules that we do. But it's not always playing a role in bigger molecules because it's very hard for big molecules to be symmetrical. But that's opening a new can of worms here when I talk about symmetrical. Either way, so that's how I do the shortcut method here. Okay? So be aware that looking for those guys, looking for a stealer. If you don't have a stealer, can you be polar? Well, technically yes. Just a little bit, not a lot. To be significant, probably not. NOF, okay, it's going to have it needs to be a significant level of polarity. You need to have one of those stealers. All right, so use the shortcut method. What do we got here? Do we have a stealer here? Yes. Partial negative, partial positive. Draw the structure and label it. So it's just like that. So a little bit of practice drawing these things out. NO2. Nitrogen dioxide. Now this one here, there's a typo on this one, so let's go nitrogen monoxide. I'll change that up. Okay. This is one of the products of engine combustion. So, nitrogen, oxygen. This is 5 for nitrogen, 6 for getting a little negative here. So, either way, we'll leave it as this guy's going to have a little bit odd Lewis structure. That's fine. We'll leave it as is. Skip the Lewis structure if you want. Partial negative. Here we go. They're both stealers. This guy is going to be nonpolar. Does it have some amount of electronegativity? Yes, because they're not the same. But it's small, very small difference. Do we have a stealer here? No. So, nonpolar. Okay, no charges on it. Here. Okay, so I just sketch all my single bonds up here. And this side's going to be right here, will be partially negative. It's going to steal from probably the hydrogen, partially positive. Okay. And moving along here. What does it mean to be symmetrical? Okay, so hopefully we've already paused out here and learned a little more about shapes and polarity and things of this nature. So to be symmetrical, I could have X bonded to X. Symmetrical could be a shape too. So X bonded to Y, that's not symmetrical. I could do X bonded to X bonded to X. That's a symmetrical linear shape. But X bonded to Z bonded to Y, that's not symmetrical. I got X on one side, Y on the other side. That's not the same. If I could do X, Z, Z, and Z. That's a symmetrical shape, right? It's symmetrical in all these axes. But if I go X, Z, Y, Y, that's not symmetrical. So there's a difference between bonded and non-bonded electrons. Okay, so we gotta know that. So if I have, let's say, X, let's use water for example here. Let's do that. H2O. All right, unbonded pair, unbonded pair. All right, so this is a domain. This is an electron domain. This is an electron domain. This is an electron domain. So oxygen has 4 electron domains, 2 of which are bonded, 2 are non-bonded. Hopefully that makes sense. Is there a shortcut in knowing if a molecule is symmetrical? And the answer is yes. Our shortcut rule, which hopefully you're aware of, is that if you have any unbonded pairs, then you are considered symmetrical, asymmetrical. Okay? And we're not going to get into this a ton because there's a little video on that. Okay? Can you remind me again why I need to know if a molecule is symmetrical? And the reason why it's important to know it's symmetrical is because if it's symmetrical, then we will have, it's a possibility that, let's say, carbon tetrafluoride, all right? This is typically we got a stealer here, okay? And if it's completely balanced, then its dipole moment is 0. So anytime you're symmetrical, you automatically default to a dipole moment, okay, equaling 0. So, in this case, even though we have a highly electronegative atom, this guy pulls this way, this guy pulls it back, this guy pulls this way, this guy pulls it back. So, they all cancel, and this thing is nonpolar. There's a little video here on how to do this, more of the shape stuff, which you're going to want to be aware of. Okay, so on this atom, now we're assuming you've taken a little break here and learned a little more about our shapes. So we're not going to go into that in this thing. And the hybridization, there's a whole note-taking sheet in this, so make sure you get on that if you don't know. But this thing here, what's the shape of X? Atom listed below, describe the following Y and X. Okay, so what's X? X has got 4 electron domains, 1, 2, 3, 4. It's tetrahedral around X. What's electronic shape? It's also tetrahedral. And hybridization, sp3. 4 things, 3, 4. What about Y? All right, 4 things, 4 electron domains, 1, 2, 3, 4. But since only 2 of them are bonded, we call that bent. It's bent around Y. The electronic shape includes all domains, so 4 things, tetrahedral. And 4 things, 4 domains, 4 things, sp3. All right, and there we go. There's our answers. Moving along. Just again, PowerPoint. There's other resources on these shapes. Shapes are important. Okay. Hydrogen bonding versus dipole-dipole. All right, so we have a stealer, NOF, and when they're bound to a hydrogen, then we call it hydrogen bonding. But again, be really important that this bond right here is a covalent bond. That's not the hydrogen bond. All right, this becomes partial negative, this becomes partial positive. Therefore, like for example, in ammonia, All right, now ammonia looks like this. NH3, it's got a pair of electrons there. So it's got a partial negative and a partial positive. So when I try and model this out, how do I show hydrogen bonding? Well, I have another nitrogen here. Hydrogen, 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 and of course, the hydrogen bond is actually right here. And we would never show a dash on that, we would just show dots. That's the hydrogen bond. Okay, dipole-dipole is when we have a stealer, N, but it's not hooked to a hydrogen. O and F. So now this becomes partial negative, this becomes partial positive. Some other substance equals some other atom, not a stealer and not a hydrogen. So in that case, you just get a general molecule, with a partial negative, partial positive. We know this is one of our stealers, for example. We don't know what this is, but it's not a hydrogen, and therefore we get attraction to something else. All right. Okay. So very similar. All works the same. All right. So rounding down the end here, hopefully soon. It's a little bit longer video. It's a big topic. Introduction to intermolecular forces. All right. So we always want to schematic this stuff out. Ionic compound. What breaks when we melt an ionic compound? When an ionic compound breaks. All right. What are the factors? Charge and the internuclear distance. Or the size of the atoms. That's based off of force equals charge times charge divided by distance squared. Okay, covalent bond. What breaks when you melt this? We get intermolecular forces. Okay. So, one of the first things we look at here, what will eventually be coming along here is okay, do you have a dipole moment? Do you have a stealer? So there's a couple of ways we could sketch this out. Sometimes we look at this. We say ourselves NOF. Okay? And you could say to yourself, okay, do I have one of these? Yes or no? If the answer is no, well, then we likely will be nonpolar. Okay? If the answer is yes, now we got to look at shape. Right? And are you symmetrical? If you're I'm going to get rid of a little more of those yet. Let's put, if it's yes, then we go to symmetricalness or asymmetrical. So are you symmetrical? If the answer is yes, then once again you cancel to be nonpolar. If the answer is no, then you are polar. And we'll spend a bunch of time looking at all this stuff in class. This is a really huge idea that we want to make sure we really have under our belt. All right. Again, sort of an idea what it looks like. Again, I just highlighted hydrogen bonding versus dipole-dipole because, well, it's an option there. So one or the other. And there we go. Polar versus nonpolar. Requirements. Take a look. Student hypothesis. When ice is vaporized, bonds between hydrogen and oxygen bonds are broken, just very nullified. So we're saying that ice, when we break this thing, these guys break right here. And the answer is nullify. And why is that? Because all we're breaking actually is the intermolecular attractions. Water in the air, all right? As you're sitting here, there's all sorts of stuff floating around the air, water-wise. That little water molecule looks just like that, okay? Can you model hydrogen bonding? Add 3 water molecules. Okay, so water. And I would want to show the position of these things. So I might go like this. Or like this. And you don't typically have to label it, but you could put dots if you'd like. like that. All right. And another example would be if we have ethanol. How do you show dissolving of water in it? Well, we could go like this. Definitely wouldn't want to show a dash here, but you could do dot, dot, dot if you wanted to. All right, I'm going to take that off there because you can't see it real well. All right. All right, there we go. Notice the negative end is by the positive end. This is partial negative, this is partial positive. There you go. I could also draw a water molecule here. There we go. All right. And this looks at our last part here. Okay. We have three different types of interlayer forces. We have dipole, which is generic two dipoles attracting to each other. Another version of that is called hydrogen bonding. And our last one's coming up in the next video, which is called the London dispersion force. All right, thank you very much.